Okay, so we are on. Brian, the floor is yours. Thank you so much
Cool.
again for taking your time to do this. Yeah.
Yeah. So, hi everybody who I haven't gotten a chance to talk to yet. So I'm Brian. I've been teaching some of the courses now with Quantum Formalism Academy. We did recently the crash course for group theory and topology to get into this Lie group specialization course where we're doing applications to quantum mechanics or quantum computing and machine learning. And then after this, we're also going to be doing a topological data analysis course, which is kind of cool. So recently in the news, they announced the Abel Prize for mathematics. It's like the Nobel Prize for math, sort of like the non-discriminatory one where it's open to like the lifetime career of a mathematician, not just the people who made these contributions under 40. And so the winner for this past year is Masaki Kashiwara. He's a Japanese mathematician who made foundational improvements and results to this field called algebraic analysis and representation theory and mathematical physics. Very cool stuff. So I was really interested to give it this kind of overview talk on his work because it sort of influenced my whole mathematical career. My PhD was all in work that he did on micro-local sheaf theory. We'll talk a little bit about that near the end. And then toward my two postdocs I did, first at the University of Wisconsin, and then later on in Paris at Institut de Mathématiques de Jussieu. I worked in algebraic analysis and Riemann-Hilbert correspondence, which are again things that Kashiwara has sort of spearheaded. So yeah, so let's get into it. So I tried to make this talk as kind of general audience as possible. Given the subject matter, it's a little difficult all the way through to do that. I kind of have to assume that you guys have seen some calculus. We're going to talk about like differentiating things. Some linear algebra is really helpful, and anything after that is just gravy. Anything that isn't that stuff, we'll talk about it in more detail. Okay. The first thing we'll talk about is D modules, which are sort of jumping all the way up into like graduate math, but we'll kind of explain it more intuitively, I hope. So interrupt with questions if you have them. If you type them in the chat, hopefully Bombordy can alert me to it because I'll be in my slides. But yeah, let's get into it. So I really liked how there was this kind of non-specialist announcement of the Abel Prize calling Kashiwara as this bridge builder across mathematics. I think that's really apt because he connected a lot of different domains and showed that they were just different versions of looking at the same problem. You'll hear often that there are really three big branches of math, like algebra, analysis, and geometry. And as in many things, this is really an illusion. The further you get into the subjects, the more you realize that they're just talking about the same problems from different perspectives. Just a neat graphic for, the Abel Prize. It really is the Nobel Prize for math, where you get to, celebrate the lifetime achievement for a mathematician. So we're talking about a few of his main contributions. We won't get to talk so much about the representation theory stuff at the end. This is his work on like crystal bases, representations of quantum groups. That's a little bit out of my wheelhouse, but I'd be happy to point people in the right direction if they're interested in that kind of stuff. Kind of related to representations of compact Lie groups, but a little bit more so. So we'll talk about D modules, which are this sort of algebraic way of looking at things from analysis, particularly like differential equations. After that, we'll see how analysis kind of corresponds to a topological picture via something called the Riemann-Hilbert correspondence, which Kashiwara proved two huge versions of, like 40 years apart. And then we'll talk a little bit more about the geometry of this analysis in a way that's kind of maybe like fully into the topological picture of the Riemann-Hilbert correspondence, which is a micro-local sheaf theory. And we'll kind of talk throughout about the impact of all these works. So if you've seen some calculus, differential equations are everywhere. If you've been in physics or engineering, you've seen differential equations everywhere. I think it's not unreasonable to say that like every physical law is expressible, at least in terms of differential equations. They describe the process of change. And, they're not really necessarily like your equations from, you know, pre-algebra or just algebra itself, where, you want to find specific values of x that solve your quadratic equation. A differential equation is an equation like involving a function and its derivatives. And your solution to this thing is a function, not like a set of points. A typical first example you might encounter is the exponential function. So this is an example of a, first differential equation. You're looking for some unknown function f who is equal to some, that's equal to its own derivative, or maybe equal to some scalar multiple of its derivative. So one of the, big things about the exponential function and the base e is that it satisfies this equation. So when possible, you want to find an explicit solution to these things, or an explicit function that realizes this equation. But not everything is nice. You can't always find an explicit solution, even when you want to. Sometimes you have to use numerical methods, and that's really come a long way. Even in machine learning now, there's this physics-informed neural networks that are really good at solving differential equations numerically. But there's other ways of approaching these things. You can treat differential equations using algebra or abstract algebra. So this approach was really pioneered by Kashiwara's advisor, Mikio Sato, in Japan. I think this is when he was in University of Tokyo. So they're using like the algebraic structure of differential equation to understand the solutions to their equation. You can kind of see this maybe back if you do some differential equations in calculus, you might try to find like the characteristic polynomial of a constant coefficient system, and you find the eigenvalues of these things, and they tell you exactly what the solutions are. And this is kind of an analogous type of strategy. So this whole field ended up becoming something called algebraic analysis. It's really kicked off, I think, by like Kashiwara's master's thesis, which is sort of insane. So the starting point of this whole field of algebraic analysis is that you treat differential operators, or things like, ddx or ddy, as algebraic objects in their own right that you can manipulate. Just like you would treat, when you start going into algebra, you think about, unknowns as some kind of variable that you can manipulate. It's very analogous. So a D module, this sort of central object of study in this field, is essentially a system of differential equations. You can think about it as like a vector space, but your sort of coefficients you're multiplying by are differential operators. So we'll go into a little bit more detail here, but a D module is like a thing, it's some kind of algebraic object where it makes sense to multiply by a function or a polynomial and differentiate elements of these things. And algebraically, in a lot of cases, these just act like polynomials themselves. So a ring here, don't worry if this is not something you've encountered before. A ring is like an algebraic gadget where it makes sense to add things and multiply them together, but maybe in a more abstract setting. So like the integers are a ring, but so are square matrices. The multiplication doesn't have to be commutative. This is kind of an important consequence. So this ring D is essentially like polynomials in our usual variables, but also allowing powers of differential operators, usually with complex coefficients, because everything's a little bit nicer with complex numbers. Hopefully it's not too weird. I'm kind of just assuring you that it's not so weird. The simplest example of this thing is something called the Weyl algebra. And you can kind of see this in quantum mechanics. So this is, so it's like a Lie algebra. It contains the Heisenberg algebra, it contains the matrix Lie algebra, SL2C. It's a non-commutative ring. So the multiplication between Z and D dz doesn't commute. And the degree to which it doesn't commute exactly comes from the product rule from calculus. So this thing really arises from the fact that if you, multiply some unknown function by BDZ, apply the differential operator, and then multiply by Z, it's not the same thing as multiplying by z and then taking the derivative. The difference occurs exactly because of the product rule, and this is what this kind of rule is abstractly representing. More generally, if I take any other polynomial, the degree to which d, dz, and f don't commute is exactly the partial derivative, or the derivative of f with respect to z. So when I'm talking about a module over this collection of differential operators, it's some algebraic gadget where we can, add and subtract things in it. It's like a group, if you've seen that, or kind of like a vector space, where it makes sense to like add and scale things. But now by scaling things, we can multiply m by any polynomial, and I can also differentiate elements of m. So before we get kind of too far afield, you get really clear examples from just taking polynomials. I can always take a polynomial and multiply it by another polynomial. I get a polynomial back. This is just kind of notation for all polynomials in one variable with complex coefficients. And another more general thing in dimension one is complex differentiable functions in one variable. So these are kind of your functions on the complex plane, which you can take d, dz of. So it contains all of our polynomials. It also contains things like the exponential function, sine, cosine, trig things, and logarithms sometimes also. So it gives you kind of like a more flexible solution. So a lot of times what we'll look at in the world of D modules is like, what are our solutions in given spaces? Maybe you'll look for polynomial solutions, or you look for polymorphic solutions. So, but we have a little bit more flexibility with just this kind of framework. Part of this language lets us kind of push the rules a little bit. We don't have to just consider functions as D modules. So I'm going to take a differential operator, p, which is just like the square of d dz. It's applying the second derivative to something. And I'm going to form this so-called cyclic D module generated by p. So I'm taking my collection of differential operators, and I'm sort of killing off anything that has a term of d squared by dz squared out of it. So algebraically, we'd write it like this. But in effect, what this is doing is, well, I can write any kind of element in this ring D as some polynomial in with no differential operators, or with differential operators of degree 1, or differential operators of degree 2, and so on. So what this rule is doing is we're just sort of setting all the things with d squared by dz squared equal to 0. And in effect, this tells us we only have really two independent variables here. We have one copy of complex polynomials for each degree of differential operator we're allowing. So algebraically, we would say this module has rank 2 over complex polynomials. This is kind of analogous to saying a vector space has dimension 2 over the reals or the complex numbers. Changing the coefficients can change, what sort of rank this thing might have. If I consider this thing as a vector space, I can add and multiply polynomials. This is an infinite dimensional vector space. But this rank here is not some kind of weird thing. It's really related to the fact that I can consider this as a differential equation with solutions that are two-dimensional. Right? If I take my differential operator I started with, p, and I apply to some unknown function, well, the solutions to this differential equation are exactly things whose second derivative is equal to 0. Right? So there's some constant term, and there's some linear term. So the space of solutions is a two-dimensional vector space over the complex numbers. We're kind of back into reality a little bit, out of algebraic land. So this correspondence between the D module having rank 2, the solutions being dimension 2 is a very deep correspondence. This is related to the Riemann-Hilbert correspondence, whereas we're going to see later. That you can really kind of recover one side from the other. If you know what the structure of the solutions is, provided you have some kind of conditions on it, you can exactly reconstruct a differential equation that would give you those solutions. And so in a sense, you got like your topology over here, and you have your algebra or analysis, and they are bridged. In general, I could take some differential operator or linear differential operator. So they would all look of this form. So there's like some polynomial where each of the coefficients is itself some polynomial, and then they are arranged in like increasing order of differentiation. Then I can look at the solutions of P, let's say with these complex differentiable functions. So this is a little bit in the weeds, but as a kind of a link to what might go further on from here, I can write the solutions of P. So this is like PU equals 0 over here, as D linear maps from this D module generated by P to O, which is our complex differentiable functions. The fact that this thing is D linear means it's like maps from D to O, which send dp to 0. With a little bit of extra work, this is exactly the set of solutions to P. This might seem like kind of algebraic faff, we're kind of rearranging things in different ways. But the point is that we can start connecting these to different fields. So in particular, like this framework right here, writing this thing in terms of some like Hom set or set of functions, connects us to tools from homological algebra. This is sort of like nonlinear algebra. This is where you get like tools in category theory. You can study obstructions to solutions existing as kind of higher algebraic terms. So not only do they let you like rewrite solutions, they also tell you stuff about the properties of those solutions, like where they might be singular, or you can think about them as like blowing up or behaving strangely. Maybe the behavior goes to infinity, and how fast it goes to infinity, and so on. So the appropriate language from this, if you kind of have any sort of geometric background, is something called sheaf theory. We're not going to go into a ton of detail, but we're going to express it in the framework of it lets you glue local data about solutions into global data about solutions. So if I know how the solution behaves near each point of some space, I know how it behaves everywhere. It sort of glues together. So, as an example, for ordinary differential equations, ODEs, your solutions are always finite dimensional, right? There's always like a finite basis of solutions, assuming that you have finitely many ordinary differential equations. Something interesting happens though in the complex domain. So some people from our Lie groups course have already started seeing this phenomenon of analytic continuation. It's like a strong property of gluing for complex functions. If two complex functions agree on some open set, then they agree everywhere, provided that you connected space. So you look at the property of your solution on some little ball, you look at it like a neighboring ball, and these solutions must be the same then if they overlap. So you follow this in a little path around your space, and you end up with this interesting phenomenon called monodromy, that if you follow the solution around some kind of closed path around some singularity, you end up with a solution different from the one you started, but maybe isomorphic to it, or kind of equivalent to it up to some structure preserving way. So we'll kind of start talking a little bit more about this geometry in terms of our topology. So the way in which these solutions start interacting with the topology of the underlying space is what is really the heart of the Riemann-Hilbert correspondence. So we're going to take another differential equation, another kind of D module. So this one, we're looking at z df dz equals alpha f, where alpha is just some non-zero complex number. So this thing has a singularity at z equals 0. You'll notice that if I want to sort of clear this side, this looks like alpha over z times f. It's a manageable singularity or a tame. Sometimes we'll call it a regular singularity. And let's see sort of what's going on here. So if you do a little bit of calculus, you can see that this general solution is, some constant out front, which we don't really worry about, times z to the alpha. So if alpha is, a positive integer, this is just a polynomial, all is kosher. We don't have to worry about anything. If alpha is a negative integer, it's a little weird. You get things like 1 over z, but these are still fairly well behaved. They're well defined everywhere. But when alpha is a complex number that is not an integer, and then suddenly you're raising a complex number to a complex power. And this is not necessarily a globally defined function. And the issue is that you have to use the complex logarithm to really define this. If you guys have ever done any kind of complex analysis or like calculus with complex numbers, you might encounter this sort of expression. Now, the issue is that for complex numbers, the logarithm is a little finicky. It's a multi-valued function. So the logarithm of a complex number is, the usual log of the absolute value of z plus, the complex number I times the argument. So this is the angle it makes with the positive x-axis plus this extra sort of ambiguity term. This has to do with the fact that e to the I theta is sort of periodic. If I am only sort of caring about the angle that I make with the positive x-axis, then 0 degrees is the same thing as 2 pi, is the same thing as 4 pi. And so if I'm asking for the logarithm of some number, I'm asking for what angle gives me that particular z value. But there could be infinitely many of them. The way you usually get around this is by doing something called a branch cut of the complex numbers. You sort of restrict the domain. So you sort of say, the logarithm is defined for only these values of theta between 0 and 2 pi, or between minus pi and pi. So you can define it kind of globally, except for some like ray. So the issue is like this, I can write this expression, but the same expression isn't valid everywhere at the same time. So this is what we're saying, that it's not a problem to write this out, but you have to pay attention to which domain you're talking about. So this is, at each one of these little open sets here, these little kind of orange balls, this is perfectly well defined at each step. But then as I travel around the circle, suddenly I run into the problem of the ambiguity here. I pick up an extra, 2 pi in my angle, because these things have to agree. But, this is the issue. This is this extra factor called arising from monodromy. We can find a local solution on each one, but we want to be able to glue them together. By continuity and by analytic continuation, they already glue for us. But when I kind of travel around from Z to, oops, there should be an E right here. That's a little typo on my part. We find that I get an extra factor of 2 pi in my logarithm. And so that sort of pulls out to an extra factor of e to the 2 pi I alpha in my function f hat. So this multiplication by this kind of invertible number or invertible matrix in higher dimensions is called the monodromy of the differential equation. It tells you the structure of the solutions as you travel around singularities of the system. The cool thing is that this study of monodromy doesn't really have to be restricted to just differential equations. It comes up in its own right in topology or algebraic topology, where you care a lot about studying the behavior of all these loops in a given space. So what this structure is kind of coming from, the structure of behavior as you travel around different loops, is captured by the fundamental group of a space. For those of you who don't really know about groups, this is sort of an algebraic property that keeps track of symmetries. So the fundamental group keeps track of the behavior of holes in your space. If I have, just say, the complex plane by itself, the fundamental group is 0. Every loop is essentially the same thing as a constant loop. I can always sort of shrink them down to a point without running into any holes in the space. For the complex plane minus a point, there's sort of one loop that encircles that point up to continuous stretching and deformation that can't be ignored. And so the fundamental group of the complex plane minus a point keeps track of that one loop. And you go around the loop once, twice, and so on. It's a group under concatenation of paths. So here I've drawn a picture of the sphere with 3 points removed. There's 3 red points. And so each of these individual things would be an element of this fundamental group, the gamma 1, gamma 2, and gamma 3. And you would concatenate these things or multiply them together in this group by going, first I go around gamma 1, and then I go around gamma 2, and then I can go around gamma 3. And this forms another loop in my space. We care about it a lot because it's something called topological invariant. It helps us distinguish different spaces. So if 2 spaces can't be deformed into each other, their fundamental groups will be different. Or rather, I should say, if fundamental groups are different, then they can't be deformed into each other. It's sort of a one-way direction here. So this is kind of an abstract group, but when we want to represent this thing with concrete operations or concrete matrices, we have to go to represent a representation of the fundamental group. So in this specific case we're just talking about, the differential equation we started with, the data of this is equivalent to a representation of the fundamental group of C star, or C minus 1 point. So where I send sort of this loop around the hole at 0, gets sent to the invertible complex number, Z goes to 2 pi I alpha times Z. So this goes way back, Riemann observed some of these things on Riemann surfaces, like the sphere, and Hilbert sort of added this into his list of 23 problems in 1900. These were sort of a challenge for the next century. A lot of these things have been solved now. There's still some unsolved ones. The Riemann hypothesis is one of those. So this particular equivalence or conjecture equivalence at the time was Hilbert's 21st problem. Does every representation of the fundamental group come from some monodromy representation of a differential equation with, mild singularities? They called this, mild singularity class Fuchsian classes. So much later on, in a much greater generality, this became something called the Riemann-Hilbert correspondence. So Kashiwara there are many people along the way who improved a lot of these things, in dimension 1, and then in some cases in higher dimensions, Deligne was a huge name in this field, Pierre Deligne. But if you want to say, who's the final name on the ledger that solved these things, you're going to run into Kashiwara several times. So, as I was saying, this problem originally only kind of considered differential equations on the Riemann sphere, or in general, Riemann surfaces. These are like your compact connected complex manifolds, if you care about that kind of thing, or you could think about it as spheres, a torus with 2 holes, and so on. But after not too much work, this correspondence was seen to hold in a lot higher generality, or greater generality. In fact, using D modules, or even just integrable connections, if that makes sense to you from physics, maybe, you can talk about this correspondence in arbitrary dimensions on kind of much more general spaces than just, say, the affine space, C to the N, or a Riemann sphere. In these general situations, like a complex manifold, then a D module is really just equivalent to a linear partial differential equation with some mild constraints. You could also define D modules on spaces with singularities, where the space itself is not smooth. This is using another one of Kashiwara's results, the Kashiwara embedding theorem, or Kashiwara's equivalence. So if you guys have been in any of my prereq classes or the lead groups class, I always have a horde of horribly niche mathematical memes, but I had to include this one. I found this on a Facebook page like 8 years ago, and I had to include it. What Kashiwara's equivalent says is that D modules on some maybe singular closed subset X are equivalent to D modules on an ambient smooth space Y whose support is contained inside X. And so in this case, you can always consider anything on like a not smooth space as living on some ambient smooth space, but you're only restricting your domain to that singular thing. This is nice because on not smooth spaces, you have to be very careful about what you mean by derivatives. So as an overview, the Riemann-Hilbert correspondence provides a fundamental bridge between two big fields of analysis and topology. So for analysis, we've got our linear PDEs with like tame or regular singularities that are restricted to some closed subset by sigma of X. These are captured by regular holonomic D modules. We'll talk about these terms in just a sec. And on topology side, we have how these solutions behave when they encounter, they interact with the solutions, the singularities of the differential equation. And these are captured by the representations of the fundamental group, where you have your space minus a set of singularities, and you're looking at invertible complex matrices to represent them. More generally, kind of the statement that Kashiwara actually proved relates constructible sheaves to this thing, or perverse sheaves to be more specific. I'd be happy to talk to you guys more about these terms later if you'd like. My whole PhD was in perverse sheaves. Unfortunate name that really means the antithesis of transverse, not perverted. There's a whole math overflow discussion about that. Sorry. Question?
I know, it was just me laughing about the choice of the
I know.
mathematicians.
Yeah, so it was like, so two things meet transversely if like their tangent spaces kind of intersect in a nice way. So like two lines intersecting 90 degrees is transverse. Two lines overlapping like this is not transverse. So when you want to study how subsets intersect in algebraic topology, for singular spaces, they had to have some kind of measure of the deviation from this transversality, and they called it a perversity. And then, 50 years later, we're just stuck with the name.
I mean, mathematics is a language of its own, so it doesn't need necessarily to align with our own natural human language. This is actually a good example to why one shouldn't find analogy between a mathematical term and colloquial, mundane things. They might be completely different meaning for sure, and motivation as well.
Yeah. There's a fun little adage that perverse sheaves aren't perverse and they're not sheaves. They're in fact like really, really natural objects from topology, and we'll see that maybe a little bit later on in this.
This reminds me, actually, this is a joke, by the way. I'll let you. There was one guy who plagiarized a paper, and he took the word complex Hilbert spaces as literal. So in his plagiarized, he put complicated Hilbert space.
I love that. Complicated Hilbert spaces, yeah. So what is the actual Riemann-Hilbert correspondence? So what Kashiwara proved, so this is in 1984, but although he did announce it in 1980, is an equivalence between two categories of in mathematics. So one was this category of regular holonomic D modules, and then this category of constructible sheaves on X. It's worth noting that there was another proof that came out independently in 84 by Zogman Bedput. But if you say that around Kashiwara, be prepared for glares. Kashiwara had this proof a few years earlier. But this correspondence is given by sending a D module M to its space of solutions. So this, you'll recognize this as kind of a more general statement of the previous solution expression we had earlier. For D modules like this, more general, you can always think about them as like finitely presented, where they look like the co-kernel of two things we saw before. This is again how you need like the abstract algebra to really pull apart this equivalence. So this definitively answers Hilbert's original problem in arbitrary dimensions. So this is for any complex manifold X, which is pretty cool. Arbitrary dimensions, arbitrary regular singularities. So again, you can't just take any D module and get this sort of this characterization. So you need this property called holonomicity. So these are really the appropriate generalization of ordinary differential equations, where you have the fact that locally your solutions have fine dimensional solution spaces. So this comes from like their characteristic variety is Lagrangian, or it has the smallest possible dimension, the dimension of the ambient space. So all the examples we talked about in this talk so far are holonomic. So the one that's just our sort of not so simple one, as was like the monodromy case we studied. They also have to have regular singularities. So here's what we're talking about, like this tame property. It's that even if you have a singularity, the solutions don't grow too fast as you approach the singularity. You have at most polynomial growth in the distance to the singularity. So like this gives you things like z to the alpha, maybe times some logarithm terms. And it excludes explicitly things that have wild behavior, or things that have, you know, essential singularities, or e to the 1 over z near your singularity. Again, the first equation we saw had a regular singularity. If we take our D module M as before, it has no singularities on the complex plane, but if we want to compactify it, consider the point at infinity, you do have a regular singularity at infinity. So these are the things that are kind of algebraically manageable. It's not too bad and still can be kind of described within the realm of algebra. So we kind of talked about this already. I can sort of get through this. This property of monodromy is quite interesting because it's not quite like equivariance, as we've seen in our Lie groups course. It's something a little bit more. It's like, you know, if I change the input value of z, then the function jumps by some other amount. You know, that other amount comes from some element of the general linear group. So if I've got a system of n equations, then my solutions will be locally away from singularities in n-dimensional vector space. You know, if I've got like a degree 2 differential equation, my solutions should be a 2-dimensional vector space. And if I travel around some singularity, then I get an automorphism, or I get, you know, an invertible matrix describing how these solutions kind of transform. So the process of assigning matrices to these loops is exactly what gives you a representation of the fundamental group. If I go around this loop, then this happens to my solutions. Constructible sheaves, and maybe perverse sheaves in general, are, I hesitate to say like a more elegant way, but definitely a more sophisticated way of packaging this process together. Of, you know, the solutions are locally constant, but if I cross like a bad point or, you know, bad stratum, then the data might jump by some fixed amount. Regular singularities, unfortunately, don't cover everything interesting. A lot of really interesting equations you come across have irregular singularities, or things that might have maybe essential singularities in their solutions. So some very normal ones are like the heat equation has a singularity at infinity, or time equals 0. The area equation for optics has an irregular singularity, and same with the quantum harmonic oscillator. That's another irregular singularity at infinity. The issue, you know, you can talk about irregular singularities from the perspective of D modules, but when you go to the topological side, just talking about the monodromy isn't enough information to reconstruct the differential equation anymore. As a really simple example, you take these two differential equations right here. So on the left side, we talked about this one already. This was so the case where alpha is 1, so the solution is just z, right? Or sorry, 1 over z. But now, I actually want that to be a plus. But on the right-hand side, now suddenly our solutions are exponential, right? They've got like an e to the z or e to the 1 over z, depending on whatever the sign is supposed to be. So they both have the same monodromy where, it's the identity as you go around the circle. But one has a removable singularity and one has an essential singularity. So you sort of get this like wild behavior as you travel around it. So the regular Riemann-Hilbert correspondence kind of fails. We need more subtle data to really capture what's going on. And this comes from something called the Stokes phenomena of differential equations. So this was first investigated in like 1850s, I think, by Stokes. This picture actually comes from a little bit later from another textbook. But it describes the Stokes phenomena of the area equation, where you've got these two independent solutions. I think it's like z to the 1/4 power times e to the plus or minus 3/2 power, or something like that, or e to the z to the 3/2. And what happens is this exponential growth of the two solutions kind of changes in growth order as you travel around the circle. So on one side, right here, one solution will grow much faster than the other one, so it dominates the other smaller equation. But as you travel through some lines, this behavior kind of switches. You can think as a simple example of this as the behavior of e to the 1 over z. So e to the 1 over z has an essential singularity at 0, like an infinite degree bad point. But if I approach 0 from maybe to the left-hand side, then this thing is asymptotic to 0. It decays to 0 really, really fast, faster than any polynomial. But if I approach 0 from the other side, from the right-hand side, it blows up to infinity faster than any polynomial can. So this kind of qualitative difference in behavior of the growth order is what characterizes the Stokes phenomena. So finding a way to kind of encapsulate this or encode it using topology or combinatorics took another 40 years. It's kind of fascinating. It took a lot of different people and a lot of hard work. So some names to call out are Deline, Malgrange, Rami, Saba, Mochizuki, many others. So some of this was accomplished in the form of Stokes structures. So you take some kind of locally constant data, like a sheaf as before, where you fix the set of singularities, and you can view this changing growth order as some kind of way to filter your solutions, and the filtration changes as you move around the singularity. So this is really good for fixed singularities in low dimensions. I think like Deline, as we called out before from the regular Riemann-Hilbert correspondence, had a version that worked for dimension 1 back in the 80s. But making this work for arbitrary singularities in arbitrary dimensions took much, much more work. And they found this was really cumbersome to work with in higher dimensions. So Kashiwara and Shapira and Andrea Daniolo came up with this framework of enhanced in-sheaves, jargon proliferation. They worked in every dimension for arbitrary singularities. So this was Masaki Kashiwara again and his collaborator Andrea Daniolo put this together. And so in 2016, they proved the irregular Riemann-Hilbert correspondence 116 years after the original question was posed. This is between polynomial D modules with arbitrary singularities and constructible enhanced in-sheaves on X. So this is a mouthful. We won't really be able to get into much detail at all about what those things really are. But at a glance, so the sort of assignment works essentially the same way, where you send M to like the enhanced solutions of M. But very loosely, in-sheaves are to sheaves as distributions are to functions. In-sheaves are kind of like limits of sheaves in some bigger ambient space. And enhance is a fun term for you add an extra real variable to your domain where you keep track of the growth conditions. So do we have enough time to even talk about this? We got some time. I'll go through this quick. So the geometry of analysis is sort of playing around this is just playing around in the topological side of Riemann-Hilbert. We spent time talking about D modules, Riemann-Hilbert. Now we're fully in topology here. So I've waffled on about sheaves a lot, but what they really do is help linearize globally nonlinear data. You've got some really complicated object you want to study from geometry, and sheaves help you patch local easy data together to understand the global structure. Hopefully that local structure is easier. In a lot of cases, like manifolds in geometry, we structure it specifically so that the local data is easier. It always looks like some kind of Euclidean space. And if you ever get exposed to algebraic geometry, sheaves are like the way of doing this. If you go into differential topology or like higher dimensional calculus, then you have other tools that are equivalent to using sheaves. You like vector bundles, connections, and all this other stuff. These are examples of sheaves. So when I'm talking about microlocal, I mentioned microlocal sheaf theory. It's a kind of an extra degree of interesting on top of this. So the sheaf data is about what happens locally around some point. And you're asking what happens to some algebraic data near some point P. If you're working microlocally on some space, you're looking at that point and what happens in some direction based at that point. It ends up being a little bit nicer mathematically to work with the like co-direction, so covectors, not vectors. But on Euclidean spaces is essentially the same thing. So you're asking not what happens to your data near a point, but what happens at that point if I move in some direction. How does my data change if I leave in that direction? So this is really interesting for like propagation of singularities in solutions to differential equations. That's how you might see it in just like a functional analysis type of perspective for PDEs. But it has a whole interesting application in topology, and this is really pioneered by the Kyoto School, Kashiwara, and his collaborator Pierre Shapiro. This is sort of what I did a lot of my research on in grad school. So you take some algebraic assignment of data, some sheaf, and you look at the micro support of this thing. So these are all the directions in which the behavior is interesting or it changes. It's not locally constant. So this has a lot of stuff that's kind of in its own right interesting, I think. So what I did my specific PhD in was something called singularity theory in complex geometry. So this was like singularities of hypersurfaces, which you can study entirely in terms of these perverse sheaves and microlocal sheaf theory. So this really gets a lot of its power from something called Morse theory. So this is why you like covectors more than vectors. So you have any covector at a point, you can always find a smooth function, or a function, it's at least continuously differentiable, whose derivative at that point is equal to that covector. And so understanding how something changes in the direction, say psi, is equivalent to understanding how the topology of the level sets change near that value. So in particular, this fundamental theorem from Morse theory is that if I've got two parameters, T1 and T2, or T1's less than T2, then the topologies of these sub-level sets are the same whenever F has no critical values in that interval. So these things kind of, the critical points or critical values of F govern how these topologies will change. And you can say even more explicitly, like if F has a single critical point of, it's non-degenerate with some index, then you attach this specific topological object to change the topology. It's a very powerful result for decomposing more complicated spaces. Maybe in one of the office hours for Lie groups or something else, I can give some fun pictures of that. There's, you can think about, say, a sphere, and your Morse function is the height of the sphere, right? So the level sets are empty, empty, and then suddenly I hit the bottom of the sphere. That's a critical point. And then I'm kind of attaching a 0 cell to it. And as I move up away from that point, the north or the south pole, the level sets are all circles. And then suddenly I will hit the top of the sphere, which is the critical point of index 2. I attach a 2 cell here. And I can glue these things together and reconstruct the topology of the sphere exactly. And so this is just kind of a throwaway, more abstract thing that this microsupport is exactly characterized by points where the cohomology of these level sets changes as I vary my input t. This is sort of like a different set of coefficients for understanding the geometry of these level sets. So these are some images I had in my thesis. If you guys stick around for the topological data analysis course coming up, so we'll talk a lot more about homology and cohomology as algebraic tools for studying kind of complicated nonlinear geometric data. So this is saying right here, like at this point P, if I move up on this axis, the cohomology doesn't change at all. It's sort of constant behavior in that direction. But if I move off of that axis, the topology does change. And so I get those points in my microsupport. And this is another picture from my thesis. So this was published in Annales de l'Institut Fourier like this last year. Again, studying how these things deform and change in different directions using the microsupport. So that's the end. I've got some references here at the end too. If you guys are interested in any of these, I'd be happy to share these.
Fantastic. Thank you so much. That was very informative. A lot to pack, I'm sure, from the audience.
Sorry. Sorry.
Yeah, no. It's cool. It's cool. I will let my questions to the end after everyone else. Let's see who wants to adventure from the audience. On stage, for example, does anyone have any question or comment or anything they want to put to Brian? Just unmute yourself and ask.
Hey, Brian. I have one question. You may have covered part of it. Yeah, so I've been kind of learning a little bit more about sheaf cohomology, and I was wondering how sheaf cohomology like ties into this picture, like being able to do computations like that with sheaves, and how it kind of ties into the singularity theory.
So yeah, that's a great question. So when you plug in, so sheaf cohomology is sort of a way of detecting the algebraic properties of this nonlinear data of a sheaf for sort of the general audience. If I'm plugging in a very general sheaf, in general, it's kind of hard to compute the sheaf cohomology. But in this context, when you're dealing with these things that are constructible sheaves, they're far easier to compute. You don't really have to do this messiness of like spectral sequences too much, which is sort of like this infinite sequence of data that sort of collapses and tells you how to compute these things. So for constructible sheaves, they're characterized by like there's some decomposition of your space, some stratification along which they are locally constant always. And so if you zoom into a space or like zoom in at some point also, the cohomology is the same thing as the cohomology of a ball at that point with the coefficients in that space. So for me, like a lot of computations boil down to like sort of bog standard things from algebraic topology, like Meyer-Vietoris, for example. That was like the main tool I'd actually really have to use computing these things.
Great, thank you.
Great, thank you.
We got George here.
Yeah, can you share the slides, particularly the last page of references?
Yeah. So Bombordi, I can put these in our Google Drive. And if you want to share them later or something.
Yeah, sure. Yeah. I think George, the echo it's coming from. Maybe you can just mute if you don't have any question. Yeah. Yeah, sure. I'll share the slides, and I think there was a typo also in one of the things.
Yeah,
I mean, it's a minor thing. It's not. It's not a thing. Yeah. Anyone on the chat? Anyone who is not on stage? Would you like to come on stage and ask or make any comment? Yeah. So we have someone. Dennis. I think Dennis is a mathematician as well. Welcome, Dennis.
Oh, hello. Can you hear me?
Yeah.
Okay, fantastic. Yeah. So hello from Abu Dhabi. I have a little question here. Do we have any hope to generalize these techniques to nonlinear PDEs?
I know that that is being worked on, but I know that it's a lot harder to capture the algebraic or topological data corresponding to them. I think some of that stuff is being done in like symplectic topology. I might have seen, but I don't know off the top of my head. I think this thing was. I remember seeing a question about that exact topic on like Math Everflow 8 years ago or something. I recommend.
But if you find something, please share, because nonlinear PDEs, this is a real challenge. Yeah. Thank you.
Anyone else? Thank you, Dennis, for your thing. It's actually very interesting indeed. My other, maybe this is more because we have machine learning people here. What do you see? The prospects of applying shift theory to machine learning, Brian?
So I think it's really like sheaf theory is just this very good principle of reconstructing global data from local data. So I saw that some of this stuff was done. There was this one paper about sheaf theory and some kind of deep learning. I don't remember who you shared that before, but I don't remember exactly who did that. But you can do this on like graphs, for example, like as an abstract representation of some topological space. You can then think about locally assigning easy data to maybe each node or each like cluster of a graph, and seeing how they glue gives you some kind of algebraic data by like, some automorphism on cycles or something. And so something I was playing around with a little bit later was kind of like, is there a deep learning version of the Riemann-Hilbert correspondence where you've got, equivariant neural networks on one side where maybe it's equivariant with respect to some Mondrian reaction. And on the other side, you've got this physics-informed neural network for solving a PDE on the other side. For certain cases, Riemann-Hilbert tells you already that these are the same problem. And so do these models learn the function, like the Mondrian representation or the solution, equally easily? I think an interesting question.
Yeah, and I think this definitely down the line motivates us to have a course on shift theory with applications.
Sure. Yeah. I know for persistent homology and like topological data analysis, this like someone did their master's thesis a few years ago on this. Like sheaves, co-sheaves, and applications is the thing I was thinking about. Where they frame this whole thing in terms of like persistence modules instead of persistent homology using sheaves. Very cool.
Yeah, it's really, really exciting. This actually aligns so much with what we've been telling about over the past few years, the proliferation of these abstract branches of maths into applied topics, and suddenly we have, the need for this, but then the computer science, the usual computer science degree engineering, at least their mathematical curriculum don't cover this type of stuff. So, the best I can hope for is to just pick a very mathematical book, right? Like you used to do in your graduate days to sleep.
I know, exactly. So like I was exposed to topological data analysis like personally through a paper that Kashiwara did with Shapira. they did a paper on persistent homology as an application of microlocal sheaf theory. You can really boil it down to the fact that how these topological cycles are birth and die in terms of Morse theory. So it's really like an exact application of microlocal sheaf theory. But I don't know how much they were focused on computing things, but it's like, oh yeah, these are the same.
Yeah. Very, very cool. Anyone has any other question before I ask my second question? I actually have another one, actually a more basic one. At the beginning, when you started, I was like, the whole thing. Okay, let me give priority to Dennis. Dennis, go ahead, please. You are the guest.
Yes,
so.
sorry, just something which happened into my mind. So, Brian, what you presented in your talk, it was everything I think on over the fields of zero characteristic.
Yeah.
Yeah. Do you know if there is something about D modules on the fields of finite characteristic?
Yes, I believe so. I think it becomes a little bit stranger because you have to talk about like what does a derivative mean? But I think you talk about it as like derivations maybe instead. And there's like the Derem space associated with some algebraic variety, maybe where you're getting rid of the like the fat points or something of the space. And I do think that there are p-adic versions of the Riemann-Hilbert correspondence. I don't know specific references off the top of my head, but I could probably find them pretty quick and put them into some chat or something.
Well, it is more of curiosity. But about nonlinear PDs, it was a real professional question.
Yeah, I can look into that.
Okay, thank you. So sorry for interrupting you.
No, it's okay. This is why we're having this, for everyone who is curious. Yeah, Jackson, please go ahead.
Yeah, so kind of along those lines, you had mentioned crystal bases like way at the beginning of the talk. I have recently run into this. I'm not super familiar with them, but in the context of representations of the symmetric group over finite fields.
Oh, cool.
Wondering, I don't know. I was wondering, what the connection to crystal bases was in this case. Even
so it's not something I'm super familiar with, but I know of a good place to find them. So let me see one sec. Oops. So if you want a great overview of these things, where is it here? Kashiwara's collaborator Shapira put out like a nice paper, like 50 years of working with him, and in it has a lot of references specifically those papers.
Okay, sweet. Thank you. Yeah, I'll send that to my collaborator, who's an expert in crystal bases.
Awesome. Yeah, it's been always something that's like a little bit more in the representation field representation theory side that I couldn't do everything, I guess, in my PhD.
Definitely. All right, cool.
Any other
question too?
Yes. So at the beginning, when you started, it resonated so much with me on like the classical Galois theory, this thing of associating polynomials with an algebraic structure. My question is, even beyond, obviously, Galois, the classical stuff has been extended to more things, more sophisticated theory with this contest of translating a mathematical problem in one field into another. And these things, obviously, that you mentioned algebraic topology, which was a tool also used to try to solve problems that are hard to solve using just topology. So my question is, how does this thing interconnect with his work with stuff like a Langland program, for instance?
Yeah, so I know there's like a geometric version of the Langlands conjecture, or I guess Langlands theorem, now that it's been proved, which is cool, where you have something like there's a correspondence between D modules on some space with like bundles on some other sort of space. It's like D modules on the space of bundles or something like that, where they're using D modules as an algebraic way of talking about like moving from one object to another one via some flow. I actually attended some talks so one of the authors of this Langlands program proof is a professor at UW, and I attended one of his talks in Kyoto a few years ago, where he talked about this exact thing, and I can try to share my pictures from the slides with you. So I know vaguely that it has to do with this correspondence of D modules on some very complicated domain, where it's some modularized space of some kind of other space, where they're using differential equations as viewed through D modules to move around these complicated spaces.
It's fascinating. That's why I'm asking. No.
Yeah.
This is the thing. It's really fascinating because, in one hand, obviously, since at the turn of 20th century, mathematics. In fact, people you probably Poincaré was probably the last universalist. Someone who who was comfortable at the time, obviously, talking different branches of math. But then suddenly, the explosion of all these different branches and specialized fields, and now then the movement to try to interconnect these things, trying to use the language of one to try to solve the problem of another branch. I found that very, very, very fascinating indeed.
Same. It's what motivated my whole mathematical career too. Is I was really interested in category theory as sort of the meta language going between different fields, and so. At Northeastern, where I went to my PhD, no one was doing just category theory. So I was like, well, you're doing the next coolest thing on derived categories for topology, studying things from analysis. Yeah. I definitely empathize with that kind of enthusiasm.
It's fantastic. Anyone else wants to make any comment or another question? The people on the chat, on the thing, on the view only. If you want to come on stage, raise your hand, or if you want to ask anything. Any question? It could be related to applications as well, though Brian is a pure mathematician, but a pure mathematician with who have his foot also on the application side. Quantum computing and machine learning as well. Yeah, there is I hear a ping. Yeah, George, please go ahead.
Oop, you're muted. There you go. One more time.
I think you are muted, George.
I have this vague idea, and I wonder if I'm on the right track, that sheaves are like the algebraic version of bundles in geometry.
They are very, very related. And in a general picture, they are the same kind of thing.
Okay, thank you. That gives me maybe bundles, sorry.
No, go ahead. Yeah.
That at least gives me some kind of handle on them from my perspective. I'm more of a geometer than an algebra person.
You can always view any sheaf as as a bundle, basically.
Okay.
Or any bundle as a sheaf, I should say.
Okay.
Maybe, the other way around. Because you can think about sections of that bundle as functions from your domain into the space of the bundle, and that process is gluing those continuous functions together. That becomes a sheaf.
Thank you.
Okay. Any other questions? Maybe I'll ask a crystal ball question to Brian. This is always dangerous. I mean, you mentioned some of the guy. I know Deline, he already won the field medal a couple of years ago, I guess. Yeah. Who do you think, who hasn't won it yet, that should win the next, not field medal, sorry, the Abel Prize?
The Abel Prize. Well, Peter Schultze won the Fields Medal, right? So I'm sure he's due for the Abel Prize then too.
Yeah.
his work in condensed mathematics is kind of groundbreaking, extending because it sort of purports to redo everything in mathematics. Oh yeah, Alain Kahn is a good one too. He's doing like non-commutative geometry and I think mathematical physics kind of stuff. Yeah, so my postdoc in Paris was on some stuff that Peter Schulze had invented, was this condensed mathematics. It's kind of like a non-Archimedean approach to doing all of mathematics in a very weird way. I think he was not satisfied with algebraic geometry trying to take over the rest of mathematics. He wanted to make all of mathematics algebraic geometry. But Alain Kahn is also a really good one too.
Yeah, he's another legend. Yeah, I wanted to ask, but I guess this is something that we can maybe another time. The connection with this work with non-commutative geometry. Any other question? Oh yeah, Dennis is saying Alan Kohn. Yeah. Okay. Brian, thank you so much for this very insightful. Okay, yeah. We have another question.
No, I didn't have a chance to meet him. No, I was working in the algebraic analysis wing. I was with Francois Lasserre. Yeah, and now I'm back over in Wisconsin again.
Well, we need to have you back in France. I always say to people, France is the spiritual homeland of modern mathematics.
I think so. Yeah.
It does have a very, very strong tradition. All these schools named after great mathematicians. Okay, so thank you so much again, Brian, for doing this. I think it was educational for everybody here, and also the motivation to go and explore some of these things like sheaf theory, for instance. So yeah, amazing talk, and yeah, everyone else who showed up, a big round of applause for Brian, and yeah, we hope to have Brian again give another talk. In the meantime, you can attend his courses. He has one on Lie groups with applications, and there's one coming on topological data analysis with applications as well, where he will elaborate some of the stuff that he's mentioning. So yeah, thank you so much. And I forgot to stop. I need to stop recording. So those on YouTube, bye for now.